Hello and welcome to episode 2 of my Let's Make a NES Game in C video. So in this video I will build on the code from the last video and we will dive into some more complicated stuff as we go. One of the key things with most games, all games probably, are the inclusion of like a coding practice, if you like, or recognized paradigm called state machines. It's basically a way of recognizing a load of actions that need to be carried out, kind of grouping them together and having like one variable or way of controlling the states. I'll get into simple ways to implement this in a bit. Basically, you use them for like everything in games, and I'll highlight some of those as we will find them in the code when I go into it shortly. Another thing I'll sort of talk about as well is how you can implement destructible backgrounds as well. As in the Invaders game itself, we obviously have the bunkers which the player can hide underneath when the invaders are dropping missiles down on them. I'll go into how I've implemented that here and how you can implement it yourself using, if you sort of need it for a project you're doing, or if you want to figure out how to do it yourself. Just like in the other video, I will be dropping functions and variables in as we go in a bit, and the key stuff I will explain as we go. And then at the end of today's video, hopefully we'll have something that resembles a mini game. My plan is to drop in most of what you could call a title screen. The full sort of structure of a main game state is what we need as well, so that in the final video we can go over in detail how the invaders actually work. So everything for the game will be pretty much dropped in today except for the invaders logic, so we can go over that in more detail in the final video. So let's go over state machines. So I've got some simple examples here, and the way to sort of handle state machines is usually with a switch block, and then usually what you would have, so in the example here is for the sort of like the main sort of game states themselves for the actual playing of the game. So here we have a game state variable which holds what state the game will be in next or is currently in. Sometimes what you do is you also might need to add a substate in here as well, which I'll show you in a bit. But ideally what you have is the game itself would normally be in only one of however many states you decide there should be. And then you would normally have in this example here, a switch block, and then depending on what state ID or number the game state variable contained would then depend on which function in this case would be called to carry out the actions of that state. So you can see here for the game we would have like one state could be new level, and then we could have a whole load of code which cleared the screen repopulated the entities which would be on that level, maybe changed some graphics, some colour, whatever, played a new sound. And this state is completely isolated from all of the other states. The idea is only one would be active at any time, and this allows us to strictly control the flow of code, so we can know at any time what's actually going on, and we can also be happy that none of these other states are having their functions called either. So from this example here, you can see, or hopefully you can see, how this state machine can be used for lots of other tasks in your game, and will be used for lots of other tasks, as I will show you various state machines, whether they are consisting of only a few states or many. And there's also there's no reason why one of these states might not have substates themselves, or their own state machine inside their function. So anytime you need to sort of break down logic into like smaller blocks of code, a state machine is probably going to be the management sort of code you need to do that. Another example here is, although this isn't used in this game here, it could be used in a more complicated game perhaps. I do have various states of our player, and one thing you could do is to implement a rigid sort of switch case block here for your player's states. I haven't actually done this myself, but if there was a lot of different states, then it would be worth implementing a switch block just to keep the code clean, so you can see at like a quick glance what's actually happening. So as an example here, again, these kind of match with the game state as a whole, and these could be sort of called the first time round, if you like. So if it was a new level at the game state, the player would obviously, if it was a new level, you'd set up the player. Then you could have one which would be play, which could have code inside for reading the joypad to move the player around. And then I've also put some examples here. So if the game was won, you could have the player do like a victory dance animation or something. And then if the level was clear, you could have a different sort of animation play. And then game over, example here, like sad face from player. So this gives you like hopefully an idea of state machines, and you can think how and where you could use these. Again, the more you sort of code around on these things, the more you can sort of recognize scenarios where you should probably use a state machine to handle the logic of something. So next up, in this game, there are obviously bunkers for the player to be underneath. These are destructible backgrounds. So as the NES creates its display from 8x8 tiles, if we are going to implement any sort of destructible background, then we need to create those using tiles. So if I quickly come to the tile set here for this game, you'll see there's 3 tiles I've highlighted here. These tiles are arranged to create a bunker. In the game, a bunker is a 32 by 24 pixel block, and it consists of 4 tiles across by 3 tiles down, if you were to think of it as being in a grid. So when you create destructible backgrounds, you want to use them sparingly, as you will need to create kind of like some layers of collision detection to know where exactly they are being collided with. So normally you would first kind of create like an outer collision rectangle or area. Always kind of think of areas or regions as a rectangular area. Ideally you would want to align them to the tiles themselves, so you would kind of think of them as being in like 8 by 8 pixel blocks. So you would align them to like 8 by 8 pixel regions, although this doesn't have to be the case. If you sort of designed a destructible block from more than just 3 simple tiles like I did here, then obviously you would have to use more background tiles to convey the degrading of that block. So usually what you have is like an outer sort of collision rectangle to say that this region as a whole has something inside of it, and then what you would have next is you would have like some sort of like grid inside, which holds not only the sort of like the tiles, but also the data to indicate the state of each sort of block, if you like. So depending on how many states each block would have, or how many sort of tiles is needed to degrade them, would depend on the data type you may need to use to represent this inside. So in the Invaders game, what I chose is each bunker has like a mini sort of grid array of bytes. So you see here the bunker sort of map, collision map if you like, has a width by height in tiles, so that is 3 high by 4 across. It's also worth noting how many bytes each collision block is going to take up as well. So in this case, that's 9 bytes that this uses. If each like block only had one graphic, then it could be worth just having one row going across as being like a bitmap of just bits. Again, lots of it will depend on how much RAM you sort of have to spare. So for example, if you one way you could sort of represent this block would be in bits. So you could have like a bit grid like that. So this could be packed into half a byte here, as it's only using 4 bits. So you could, if you only had either the state was fully there or destroyed, then you could use it like a sort of like binary sort of bitmap like that, and then just turn on bits and turn them off. However, in this case, I wasn't sure how many sort of states I might need to show the tiles in, so I decided to use bytes. So each tile block can be in any of 3 sort of, well, 4 states actually. You have the 3 visible states here, and then obviously you have the invisible or the destroyed state. So if I bring across an image to indicate here, so this could represent a state of one of the bunkers here. So you'll see here we would have 0 for that byte there. Wherever there's like a full tile, we would probably have the number in the array be 3 at that location. This tile would be 1 and this tile would be 2. So not only would these numbers represent the state of the tiles in that region, but by organizing the tiles in this order as well, it makes them quicker to draw as well. So you'll see here, if you add the this tile ID to the life values of each of these tiles in this grid, then that maps to the visual state of them as well. Hopefully that makes sense to you. So you take the graphic ID, add the starting from this point here, and then you add the life value in the grid, which would be 0 to 3, and then that allows you to quickly draw the actual bunker as well, should you need to sort of draw each like tile breakdown. So you kind of only draw the full bunker at the start of the level, and then you would only draw an individual tile if it was actually indicated as being hit, both first from the collision rectangle, which was the area outside. You would then convert the pixel into the sort of tile grid coordinates to then work out which tile it collided with, and then you would update the graphic for whichever tile. So that's how it was kind of done with the bunkers in the game. So now that I've talked about all of this, let's actually start with the project for today. So what I will do is I will start from last week's code. Which one was it? It was... oh no, it was this one here. So let's copy this project here, and then we'll rename the outer folder. So this is a quick way for you to sort of get started building off of a project that already exists. So in this case, the quickest way to get started is to just copy a project, rename its folders, and then take the code blocks file itself here and then edit that in a text editor. So obviously as I'm on Linux here, I'll be using the default text editor here. Obviously in Windows just use Notepad, and then all you want to change here is anywhere which refers to the project itself, and any potential folders as well. None of them are kind of named in this project here, so that's all good. This is obviously the actual title, and then once we've done that, save that, and then we should be able to open that up in code blocks, and then it should show vid2 here, and now we can get started. So first off, let's just make sure that this builds. So we will in fact can't do lowercase because we only have the one font set. Let's build that. There we go, video 2 there. So we don't need any of this now, so we can delete this. In fact, we'll keep the main function there. So what we will do is we'll drag and drop code in here from the Goomba Invaders project that I've pre-created already until we get something meaningful. So the first thing we'll do is we will start adding some state machine stuff. So off screen, what I'll do is I'll side by side the Goomba Invaders game that I've already created, and then just drag and drop some stuff in and explain it as we go. So first off, I will update the main header file here. So what these are going to be here is these will be the main game states. So normally what I do in the main header file is I usually have the G usually represents just a global. So the idea is the game states themselves will be able to change these values here and also be able to see them. The core functions for those are defined in main itself, and the core main states will implement these, and they will include the main header file in their sources so that they can read these themselves, but anything that includes the game class won't be able to sort of get at any of this stuff. So I'll cheat now. Usually I'll give everything, it's like a main state, I'll name it with a GS after it. So we have a title screen. You might need, on yours, make sure you change it to .c. Normally this would default to .cpp. And then you want to make sure that the header and source are in the your project here in the same place. The reason why I do this is because it creates a module and a header at the same time, which makes things nice and quick. And then usually what you would do is you kind of side by side these. So this will be anything to do with title screen here. So any time that you need a game state, usually they all sort of start like this pretty much. You include the header file from main, and then any functions in here. So these functions themselves, what they will enable is the first state machine, basically. And then usually how I start things off. Is we initialize the main state to start with the title screen initialize. So normally what I have is two sort of core functions for each of the states. We have an initialize function to basically set everything up, and then we have another function to just run the core code in that state. This also allows in each of the game states themselves to have like their own mini state machine in there. And then also in here I have like a default high score value as well. So you see this is 50. However, it's not 50, as I will explain. A bit later on. So then what we have here is we then have our switch block. And then any states, just use an enumeration. This keeps it nice and clean, and also easily extended or expanded upon, which is the key thing here. In this case, obviously I know how many states this game actually uses, but for your own projects that might not be the case. And then the initialize states. I always change the main state afterwards. So the initialized states, usually what they would do in a game is they'll just set up core things at the start, initialize local variables inside, clear away, maybe stop sound playing, hide sprites, something like that, or maybe even change color palettes. They literally are only there like one time, if you like. That's not the case in the core main states though. Usually in so for the title screen, for example, you would have, all you're doing in there is you are kind of waiting for the player to press the start button. Oh yeah, another key thing we have here as well. Is there is a value or a variable. There we go. This one here. So this will be used to implement random numbers for us. And all what happens is in the main loop here, this variable is constantly incremented, and then at key times throughout the game when we need a random number, we will just check what the value of the gticks variable is, and then use that as a source, as we never know obviously what the value of this will be. This is a quick and simple way to implement random numbers. Of course, dependent, if you need like a range, then you might need to AND it with a value to restrict what range of a random number you need. Well, I think that's everything from there. I shall double check. So that was, I think everything is out of there. Okay, so there's nothing to use from there. Oh yeah, here's a key thing here, which you need not to not forget, which is to vsync the NES in here, just to make sure that all drawing occurs, and then we wait at the end here. So I think everything is fine here. So what we've got now, we will fill out the title screen code now. There's very little that sort of goes on in this game here, but the idea is that in the title screen itself, you can think of it as basically like a manager for any sort of screens that you might need at the like the any sort of screens which aren't gameplay. So for example, if you had like a high score table or a player select screen, then you could implement like a mini sort of state machine in here and then have the logic and everything work inside the title screen here. Or you could even do like what's going on in main here. You could have some sub state functions declared in the title screen, and then have a special sort of state variable for all of the substates to occur in here. Again, that's kind of game dependent. All I have here is a define for text blinking. So all we have in here, the blink timer here, is what's used for a timer variable in here. In fact, I might change some of this just to make it more clear for you, seeing as I know that there is enough memory to spare. I will actually change some stuff out. So what I was doing previously was just using 1 byte as a timer. However, since these are used not very often, there's only a few of them in the game, it's easier to implement it as this. And then we'll have 2 functions to set these up. And all this does is you initialize it with a time delay. You call the update function and you check the result. Internally, this function will count down using the just subtracting 1 from the tick down variable. And then when that reaches 0, it will set the elapsed boolean to true, so we know that the whatever event we want the timer to time has triggered. And then we would call the reset function. So let's quickly implement these, and then I'll have to remember as we go to change any timers we encounter for these new ones. So the reason why these variables are duplicated is because in the reset function we basically copy the delay back into the tick down. So it's also always faster to copy from a variable first rather than copying from a pointer when we're coding on the NES anyway. So all we're doing in effect here is we are resetting the timer. We're taking the delay, passing it into the temp variable here. We then set the tick down back to the delay. In fact, we'll put a temporary one in here again. So that should handle that for us. So another thing to note in here is the LevelManager here. So I will just drag and drop the, in fact no, I won't, I'll just create another class called LevelManager. And then we'll go back here a minute, and then so we have that there. The anim timer will actually be a tick timer now. So let's go through here a minute. Quickly update this a minute, and then I will explain what's actually happening here. So what's happening is we have like blinking text in here. So to time whether the text should be shown or hidden, we need a timer which works on update ticks. And then we have a variable here for some Goomba sprites, which is what will be happening here. There's two Goomba sprites created using the actor structure here, which records 3 variables. So we have a horizontal, vertical position for them, and then some flags, which obviously won't really be used in here. This draw function just handles whether to press start to play, or it clears it out. And then it will also do exactly the same by displaying a high score if the player has a high score. So you'll see it uses the global variable high score, which I defined in main here. And we only draw the high score if it is greater than the starting high score. So you'll see at the start here we set the default high score to the global high score variable. Obviously you need to earn a high score first before it actually shows it. So to earn a high score you obviously need to be above the default score here. Again, this will depend on what you deem fit for that. So the draw text function in the title screen here, this just handles drawing the press start to play or the high score if you have it or not. In the initialize bit here, we set up these actors. This function here, init, this is for the input manager. In here, normally I would have like an input manager reset function, but the input manager initialize function does the same thing. So various times you want to reset the state of any key presses, all that sort of stuff, so that you don't get any false triggers when you switch states. And then as we have a lot of stuff to draw here, we turn the display off before we do that. And then here we set up some new color palettes, set a new background color for our title screen. We erase the whole screen's tiles. Obviously there's a lot of tiles. If you think of a whole screen, that's like 32 times 30, as that would be too much to do while the display is on. We obviously need the display to be off. And then there's also a function here in the LevelManager to draw a floor. And then we just construct some other stuff here. Obviously put your own name in here when you go through here. So what I'll do now is I'll populate the LevelManager code, and then we will briefly run what we have so I can show you it working. And then this will complain if I don't do this, so we'll create some stuff in there first. Let's see if we can build this now. It's because the defines aren't here, I think. In fact, this is let's Let's change the name of this a moment here, as that should be video 2. And I'll just quickly have a look at this a moment, see what graphics we have here. It's because it's not using the it's using a custom graphics from the other week. Obviously we need to change the sprites out. So we'll get rid of this bank of sprites. And we'll drop this one in, which is the correct one. Just double check this is the right one. Yep, this is what we are going towards. Something like this. So this is the correct project we are aiming at. So the issue is the LevelManager code is wrong. Oh wait, that's in the title screen, so the title screen stuff is wrong here. some small issues there. I was dropping in the wrong project. So it's exactly the same as before I was doing. Ah yes, using the we have to change the sprite bank in the assembly file as well. Let's see what it's. There we go. Now we've still got the I haven't changed the tiles here. We've got the new sprites in here, but the Goomba tiles are the wrong ones, so I'll have to change those out as well. So you see, we've got this is the core of the title screen working now. The LevelManager is drawing the tiles for the floor there. We have the palette cycler working here as well. You see the color for the font, then the bottom here is cycling. So let's get rid of the old Goomba graphics, and I will need to drop in the correct one. Let's rebuild that. There we go. I don't have a hat anymore. So that's the title screen set up there. One thing to note in here as well is the ability to start the game. So we have the main state, which will change here if the player presses the start button. So that's the title screen code here. So the core stuff in here. I think the level ID is being used in the palette buffer here to change the third color in with the level ID here. So you see when the timer elapses for the tick timer here, we reset it here and then we draw the text, and then the global variable b is just being flipped between true and false. Basically, you'll see here it's set to true at the start, and that is just being used to determine whether once this function draw is called, whether to display it or hide the text. That's very straightforward there. So now let's quickly go over the LevelManager code. So what I'll do is I'll quickly talk about some of the stuff in here. However, loads of it kind of won't make that much sense until you can kind of see it. So first off, we have a load of defines here for the bunkers. So there's 4 bunkers. What I'll do is I'll open up one of these pictures here. So this is the sort of when I sort of start designing these games, I give them their own sort of folder where I sort of play around with different graphics. And one of the things that I needed to do here was to decide on the size of bunkers. So how I did that was sometimes the easy way to sort of do these things is to use like an image here. So each of these, if I put this to pixel grid a moment, so you see this pixel grid is 32 tiles across by 6 tiles high. So initially what I did was I set out kind of like a template of how I want the bunkers to look and how they should be displayed on the screen. Obviously this is quite high, so in the end I sort of shortened it. As you'll see here, the height in pixels is 24 here. So what I also did in here, you'll see that there's blue frames representing like a region, if you like. So this also allowed me to position them nicely, so how they'll sort of be sort of symmetrically placed on the screen. And then to visualize this, what I actually did was I actually have a mini bitmap here. If you can see that, I'll zoom in a moment. So this is used to construct the map. So the collision map here this is used to sort of represent one of these, which tiles will be on and which tiles are off. So that assists with sort of drawing and constructing that. And then the defines in here. So like I said about the sort of rectangle collisions, to quickly know whether a bullet is colliding with one of the bases or even an invader, I have a variable here which not only is useful for representing where on the screen the bunker should be placed, it's also good for collision detection as well. So instead of having to check multiple rectangles first all we need to do is check whether the Y coordinate of a bullet or an invader is actually below or equal to the Y coordinate of the bases. Every sort of step you can take to reduce the amount of logic needed is obviously a benefit to you in the long run on the NES. So this is the Y coordinate in tiles of where these will be positioned on the screen, and then this is the Y coordinate in pixels. And then there's another one here which is where the bottom of the bunker starts. And the reason why the bottom of the bunker is needed is because obviously the player can fire from below the bunker. So you need to record where that starts also. And obviously that's where these values come in as well. So for the player's bullet, you would check first to see whether it's less than or equal to the bottom bunker variable. For the enemy bullets falling from the sky, you would check the bunker YP or Y position. And then these values here are the horizontal starting position in tiles. So you'll see here the first one, if you look at the numbers down here, the horizontal one is 2, which represents that one. This one represents 10, which is there. The next one is 18, which is there, and the final one is 26, which is there. So this kind of mini graphic here is a quick way for me to sort of visualize first how I want these to be positioned. It then allows me to record the actual tile coordinates here. And then there's some other positions here. So this is the these other ones here are for the X coordinate in pixels. So the reason why you use defines over computing this during runtime is obviously these are all constant values, and they'll only be sort of put in place in the code if you use them. And the preprocessor will obviously only put in the exact value. And obviously this has no cost. These calculations have no cost to us because they're pre-computed beforehand, which is important. And you see we have a number of functions here. So some of these functions, to keep them fast, they require you to pass variables to them, but the variables are global variables which must be set first before you call these. And again, the reason for that is speed, because passing variables is slow because these variables have to be passed on the stack, which is a 6502 construct in the machine's memory itself. And if we pass them on the stack, then first the NES must place them on the stack. Then in the function call, it then has to retrieve these values from the stack, which is slow, so it's faster to populate some global variables first in speed critical functions, and then also the return value is also in a global variable here as well, because returning, if you put into return value like that, then this return value is placed on the stack, which again would have a performance hit, as we obviously would need to call the hit base function a number of times throughout the game. Not only the player's bullet, but also all of the enemy bullets which are in play, and also potentially as well the invaders if they get down the screen. So the key functions are the initialize function and the initialize bunkers. So some of the stuff we have in here is a lot of different palette defines. So there's new colors for each of the potential levels. You'll see also in here we have a define which dictates or says how many levels are actually in the game. This is just a number I thought was good to sort of have, cap it at 8. And you see we have 5 different colours in here, which the invaders can be. Again, this is noted here as well. And then there's also a constant in here which handles which sound effect is played if a bunker is actually hit. So the LevelManager initialize function, what this does is it reads a global variable for the level ID to work out which color palettes to set, and then it also changes the attribute map as well in specific places. So this one here is the top line, so that the score and the text is a different color to everything else. This block here cycles through the region where the invaders start at the beginning and define a color for them there. And then this region here is where the bases live. I think it also sets the floor color as well in the attribute map, where the area where the floor will be. And then this updates some of the colors in palette number 3 here. So let's see, that's light grey. That's like a dark. This palette 3 is like a colour of greys here, it would seem. And then this one thing to note in all of my code is anything that is a private variable or a private function. Obviously, these naming types are something that's not actually in C itself, so to have these things, I usually put like a Z there to indicate that it should not be callable or recognized by outside functions and modules. So this function here just handles drawing one of these. Okay, I've closed that, so this just handles drawing one of the bunkers, depending which one you sort of want to draw here, and then you pass in the X and Y tile coordinates. And then this will also populate the bunker collision map. And then you'll see that there is a variable which records how many lives a bunker has. Which is the this number here, 12, which is the amount of tiles. So if I open this up again here, so the reality for it is so this is what all the bunkers actually look like. So the lives should actually not be 12, it should be 8. And the lives should correspond to the set pixels here. And the reason why we sort of want to record the lives is when we're doing the collision checking, if we're inside a collision area for one of the bunkers, we first check to see whether any of the tiles inside are actually alive. If they're not, then obviously there's no need to go routing through the actual collision map to try and find where exactly a collision occurred. And then these are just set up to plot the relevant bunker. So what should happen in here is obviously one of these will be set to match against whichever bunker needs to be drawn. And then this will plot the tile. And this obviously sets the relevant tile to 3 here if it is actually alive. So this here is the plot map here, and what it's doing is it's using bit flags to figure out whether a tile should be on or off, which is why the code kind of looks slightly ugly. So you'll see here GA is set to the leftmost bit, bit 7, which is 128. So you see here these are binary bits here set with the 0B to indicate that this is a byte in binary here. So it starts at bit 7 and then works its way over to bit 4 each time, which is what's actually happening here. So you'll see it's only reading X up to 4 here, and each time through this loop here, A is divided by 2, which is what the bit shift symbol is doing here. The 6502 obviously has no multiply or divide a function or mnemonic in assembly language. So if you were to get the VBCC to actually carry out division like this, then there's a chance that it could be very slow if it didn't recognize, I don't know whether it does, whether the division could be switched out for a bit shift. So if you ever need to multiply by any of the numbers which represent one of the bits, then shifting left or right is the way to go on the 6502. And then there's 2 loops in here. There's the Y loop here, which basically is the vertical part, and the horizontal part here, which just loops over the bits from the map here. Hopefully that's not too daunting for you to sort of get round. Everything else is fairly straightforward. So the LevelManager initialize function, this pretty much just sets up the colors pretty much and redraws the colors in the attribute map. The LevelManager initialize bunkers function, it basically what this does here is it strategically places the bunkers. So this might be something you might want to change on your game here. So what I did was I said if the level is less than 3, then draw bunkers 0 and 3. Otherwise, set their lives to 0. And then if the level is less than 5, draw bunker 1 and bunker 2. So bunker 1 and bunker 2 are the 2 middle bunkers. Bunkers 0 and 3 are obviously the ones on the far left and far right on the screen. So the main ugly code is going to come in the collisions. So let's I'll quickly talk through that now here. So what I'll do is I'll put some comments back in here as well, so you can hopefully get what's going on here. So there are a number of global 8-bit variables here. So you've got the G, A to D, GX to J, and then the R1X to R2H. They're basically general purpose bytes for passing things to and from function calls where speed is critical. So the hit base, it expects what you pass to it to be in the GX and GY variables, and the collision result will be returned in GA. Also, it expects GX and GY to be in pixel coordinates. So I'll also note that as well. This is one thing you have to do lots on the NES as well, is to convert from pixel coordinates into tiles often. So first off, what we do is we see whether the Y coordinate is less than the bunker's Y position. If it is, then we set GA to 0, indicating nothing was hit in return. So this here is primarily for the Invader bullets here. This is a quick way to negate having to execute any of the code below. The next is to see whether the bullet could be the player's bullet. So this checks to make sure that this position is less than the top of the collision rectangle. This then makes sure that it's inside the bottom of the collision rectangle. You see here, if it isn't, then if the Y coordinate is greater or equal to the bottom of the bunker, then it will also return. So what we need to do now is we need to transform the bullet's position into tiles. So the first thing we do is we back up the coordinates of the bullet into GI and GJ. We then subtract from GY the bunker's starting Y position. So the value what's in GY now will be between 0 and the height of the bunker in pixels. At this stage, what we need to do now is to check the X coordinate of the bullet to see which bunker it could be colliding with. So that's where the various bunker X coordinates. So this is the left side, this is the right side. So this first catch here, we'll see whether the bullet has hit the first bunker. Next, we check to see whether the lives are 0, indicating that the bunker is already dead. If it is, then we return. If not, then now what we need to do is to transform the bunker's position so that it aligns inside one of the collision rectangles for the bunker. So to do that, we subtract the bunker's left side from the bullet's X position. What will happen now is the GX and GY will be totally contained in the relevant bunker region. Obviously the other bunkers here, so that's bunker 2, 3 and 4, they all follow the same logic as the top one here. And then there is yes it is, it's a global byte pointer here. So we set the P source 8 to point towards bunker map 1, and then we call the hit base block 0 to indicate the first bunker to check against. And then what happens up here is this is where all of the collision occurs with the collision map. So first what happens is the X and Y coordinates here are converted to tile positions. You'll see this here means divide by 8. And then we also use GI and GA to be the actual position on the screen in tiles. So GX and GI will be used against the relevant bunker collision map, whereas GI and GJ these will be used to plot a tile on the screen if a bullet hits. And then the GY position here is times by 4, and the reason for that is each collision map obviously has 4 tiles across. See that width in tiles. So what we need to get at is the actual offset into the bunker collision map, which is obviously one of these here. So this is basically an array of 9 bytes, sorry. No, it's not, it is 12. In fact, no, it's not. It's actually 16. What am I doing? Let's get to where we are again. So we get to the relevant offset here. So first off, the Y tile is times by 4, so we get to the correct tile offset in the collision grid. We then add the GX position to the value here. We then add that number to the array pointer. We then read the byte at that location into GD here. If it's greater than 0, then we subtract 1 from that value. And then if it's greater from 0, then we need to draw or work out which brick tile to draw in its place. Otherwise, we set GC to 0 here. Then what we do is we write the value of GD back into the collision map here. And then we use GI and GJ, which are the actual tile position on the screen. And then we end up either erasing the tile or drawing a broken tile in its place. We then use the hit sound ID to play the relevant sound effect. And then we set GA to 1, indicating that we've if GD is greater than 0, that is, then we indicate that we have actually hit something. So I'll put that here. I think that changes to 1 anyway. Yep. So yeah, that's the only complicated code which really is in here. So with that out of the way, we can move on. So to move on now, we obviously need to fill out the game states in here. But before we can do that, we need 2 more things. We need the actual player. We need the bullet manager, and I will also set up a scaled down baddie manager just for this demo, just so there is something to actually shoot at when it's all implemented, so that this demo isn't dull. So let's start with the player here. And then we will have the bullet manager. So you see, we have it's kind of a sort of we have player states, like I said here, but it's kind of not really to minimize the variables needed for the player. I've kind of used various bit flags here, which is why these are all here, as some of these can kind of overlap. I could sort of split that out, but I won't. I'll leave it in here. So that the key ones here are these 3 here. these should be, or they could be just in a switch block if they didn't have these others kind of packed on here. This is just to kind of save memory here, because obviously the player can be alive but at the same time also facing left or also walking. On another machine I would probably have these somewhere else, but as we are limited to the amount of RAM, sometimes it's best to try and pack bits into bytes where we can. And then you'll see here there's also like a mask value here for resetting whether the player is actually walking. And then we also have a variable here for the max X coordinate of the player. So I shall now talk about some stuff with the player. So we have a width here for our player, 16 pixels, and then we have the starting coordinate, 120 by 192 pixels. Again, the easiest way to visualize these things is to use, I'm not sure whether I actually have one saved here. No, usually like I did the bunker setup here, I will sort of draw everything out as like a mini image and use pixels to represent tiles to place things to get an idea where things should start. So one thing we can replace in here is the private state timer. Replace that, and the animation timer for the player. And then what these things here are is they are byte offsets to the start of sprites. So I'll show you what I'm talking about here. So if you look at this number here, this tells you the relevant tile, graphic tile, that you are actually clicking on here. So this tile here is obviously the start of this graphic frame here. This tile here is the start of this graphic frame here. Same here, and so on. So this one could actually be removed here. You'll see it's a duplicate of this one here. But as I'm not using all of the sprites in here, it doesn't really matter. So I kind of used those values there to note the starting tile here for the walk cycle animation. So this tile here is obviously the top left of each of the starting sprites, and then again I have an array here which is the dying cycle, So these values here will be added to the sprite dying tile of Mario. In here there's various graphic defines which point to various sprites here. So you see here tile 32 is the turtle dove, or the Koopa as they later became known, which is there. The Koopa here is actually 32 by 32 pixels in size in reality, although the actual graphic area is only 16 by 24. You see we kind of have wasted tiles here. So usually what I'll do if I'm setting up starting tile locations for sprites, I will put like a common starting text on them so it's clear to see what you're actually working with. And then same here as for tiles as well, so these dictate the starting location for various font sets. There's another one here for the brick tile as well, which I think you will have seen in the LevelManager code. It's in there for drawing the tile. Where are we? Yeah, there you go, look. Depending on which life is present, we use the graphic starting tile and then subtract the value from it to draw the correct brick there. And you see we have the player speed here. This is a variable to indicate how many frames we have per direction. Not sure about that. Oh, it's tiles. Well, I don't think I have that recorded. This might not actually be used. Let's have a look. Okay, so this is I don't think that variable is actually used, or that define, as I didn't need to create separate graphics from facing the other way, as the NES can just mirror their sprites. Oh yeah, this is an interesting one here. So these numbers here are actually sprite attribute bits. So if I, in fact, if I open this up again a moment here. No, wrong one. So you see we only have him facing up and facing to the right here. The NES has the ability to flip sprites, so you can mirror them horizontally or vertically. So I made good use of that here to simulate the like rotations So here there's no attribute other than the color palette for this frame, and then this frame here is obviously nothing again either. And then next time round we apply a vertical flip tile attribute here, and then when we're back to here next time we apply a horizontal flip, and that gives us the illusion of him rotating. Let's have a look. I think it's in this one here. No, it's not in there. Where is it? I did actually draw this out somewhere. It might not be in here actually. But anyway, the way that you can, if I open this up a minute again, the way it works is this here. So if I copy this one out, so we have that frame there, and we have that one there. So to using both of those, we're able to flip the graphics vertically, which will create the fallen down one there. And then we're obviously able to, using that frame, we can mirror horizontally to create that there, which allows us to obviously have the falling effect, which you obviously won't see until the finished game is here. So we have like a rectangle in here for the player as well, a collision rectangle, which is obviously set up here to the size of our character. However, you'll notice we make it smaller, so it doesn't actually look so cheap when he's actually hit by a bullet, as if you if it was just 16 by 16 pixels, then there's a chance it might hit like an empty space area, which is why I added on the extra sort of offsets and a smaller width and height. So let's set up the animation timer there. So it looks like this one's used again in here. And again here. Or was there a reset? No, there was not. don't know if I've actually been using that one. No, it doesn't look like it. First casualty here. So I changed this in the last video here. So this is just for checking whether the player actually is collided with something here. In the last video I changed the rect overlaps function to use these variables here for the rectangle collision. So there's that one there. I think 82 it says as well. I think that should do it. Yep, there we go. So the player is set up now. Let's get the bullet manager in now. So I shall talk about this. So there are 4 bullets in the game. One is for the player and the others can be owned potentially by the invaders. So if we have a look at the bullets here, this will help us visualize. So that one there is the player's bullet, and that one there is the invader's bullet here. So there are some flags as well, or states for the bullets, just like the player. And then we have some separate defines for the bullets. So you'll see we have a width and a height. The player's width is different, so we have a different define for that one. And then we have some IDs here to indicate the starting number of the bullets in the bullet array here. And you'll see here I'm noting how many bytes each of these actors actually take up. And then there's some global variables here. So for example, the graphics there is a timer in here. Ever so often, if the mirror flag is set to 1, then the sprites are drawn with the sprite attribute bit being set to mirror them horizontally. Where are we? Here we are. So there is, before we draw the sprites, obviously as per the last video there, we obviously need to set the global sprite X and Y positions. And the attribute bits here as well. So you see here that the actor flag for the bullets, there is a flag to indicate whether it is the player's bullet or the baddie bullet. So anything with an F here indicates that it's a flag. Basically, if the value of the flag is greater than 0, then it means the bullet is alive, as well as in one of these other sort of whatever states you could sort of pack into that byte. So here, if it's alive, we take the X and Y coordinates, put it to the sprite manager, and then we work out whether the what palette we should use for the sprite and which graphic. So you see here, if it's the player bullet, we use the first sprite palette, and also the tile start for the player's bullet, which is what this one is. Otherwise, it's an enemy bullet, so we use the second sprite palette. And then the graphic is for the enemy bullet there. And like I said, the that mirror byte there, it could even be put in, it could even just be no, it has to be global actually. Anyway, it's used to indicate whether the sprite attribute to flip it horizontally is set or not. So the draw thing is fairly straightforward there. And then the functions here, so when we initialize the bullet manager, it calls its own private variable here. So what this does is it goes through all the actors and turns their flags to 0, which means that they're not alive. At the start, the mirror variable is set to false. And what happens here, so this variable here is for the enemy bullet speed. So this kind of tracks along with whichever level you're on. So this increases the difficulty of the game by adding the level number to the bullet speed. And then there's also a starting speed as well, which for the enemies is 1. And then there's 2 separate fire routines. We have the player firing and the enemy firing. So if the player fires, we know that the player's bullet here is always the first one. So I could have really done this here. Should have done that. And then we check to make sure that the player's bullet is actually not currently alive already. The player can only shoot one bullet at a time. So if the player's bullet isn't currently alive, we pack on. Don't need to OR it. We set the bullet's state to alive and set it to the player type. Although we don't really need to sort of, in fact, yeah, we do need it actually. And then we take the starting position that the player passes for where the bullet should be fired from, and then we add the various offsets. So the offsets, what they actually do is this will be dependent on your player graphic and the bullet graphic you use. You obviously will need to shift the bullet so that it's at a proper location from the player's position to the position that it will start at or be fired from. So for example, if we look here, you'll see the bullet is only 8 pixels wide, whereas the player is actually 16 pixels wide. So you would need like an offset of 4 pixels from the player's starting position to center it horizontally in the player. In fact, no, sorry, it would be probably about 10, maybe 12. It's less than that. It's already I've already worked out here the offsets. Yeah, it is 4 for each of them. So you would add the offset so that the bullet appears that it is actually coming from the actual firer and not from some other random location. And then obviously here we play the sound effect 0. Which is actually the sound effect for the player to fire here. And then there's obviously a bad fire one there, which does exactly the same, which is here. So the main difference here is we need to check against the other bullets. So what's going on here is if the level is less than 2, this bullet cannot be fired. So only after or equal to level 2 can a second bullet be fired by the enemies. And then this third bullet here can only be spawned after or equal to level 4. So as the difficulty gets on here, the enemies can fire more and more bullets. That's what this is doing here. And then there is a private function to spawn the relevant bullet. And then all that does is it basically sets up that enemy bullet, sets its alive flags, and then plays a sound effect in here. We've already seen the draw function here, so let's have a look at the update function. So this here is handling the animation very poorly. Let's put a proper one in here. So we will say let's put that to 5. So although it does the job, this will obviously do the job better. So what happens if this timer elapses, then it handles flipping the mirror X flag, and then this main bit here is what loops over all of the bullets and first works out which one they are. This bit here handles if they're alive. So you could have that there, and then depending on what bullet type, it will either subtract from the Y coordinate here, or it will add to the Y coordinate. And then it then checks to see whether it collides with a base. If it does, then this variable ZBA, which is used here to indicate the alive flags of each bullet in this do while loop. So this is where it checks to see whether the bullet hits a base. If it does, then it sets it to dead there. And then does it again here, depending on the type of it here. Ah, that's right. So it's what we're actually doing here is we're checking both the left and the right side of the bullet here. As the level manager hit base obviously will convert 1 point into tile coordinates and check that 1 point against whether it's hit one of the bases. However, as each bullet is either 8 or 6 pixels wide, we obviously need to check both sides of the bullet to see whether it's hit the base, which is what's happening here. This handles hitting the left side. So if we've hit the bullet on the left, the base on the left side, we obviously don't need to check the right side. If, however, we haven't hit the base on the left side, then we need to check it on the right side here. And then once we've done through and checked everything, we then plug back in the local variables BA into the actor's flags and BY into its Y position. So that's the update. There's also another function in here to handle bullet-to-bullet collision. So let's make sure we've got this one working. So you'll see here, first off, in fact, we could just do that afterwards actually. Because what this is doing here is we're seeing whether the player's bullet is actually alive first. If it's dead, then there's no point checking for bullet-to-bullet collisions. So you notice here that the R1, the first rectangle is set to the player's details here, but the second one at the start here, we only set up the bullet's width and height, because the second one is obviously just going to be the enemy bullets. So we obviously need to keep setting those up. And then check to see whether each one, if it's alive, collides with the player's bullet. If it does, then we play a sound effect for that happening. Set that bullet to dying, and then we also set the player's bullet to dying as well. And then we obviously subtract 1 from the max bullets. All this does here, it just breaks out of this loop here. So we could have just done this instead. I think that's all in there. Let's double check. Nope. What have we done? So the rect overlap function is the issue. Here we go. Okay, so it appears that the bullet manager is working there as well. So the only thing left for us to do is to try and get something actually worthwhile happening. So what we are doing here is we are setting up the game's states itself. not to be confused with the main states, which is what these are, as they are the states in the main loop, and these are the game's states for playing the game itself. Also here you'll see we have a number of messages for the player, and there is also a sub-state type as well. And the reason for that is each of these states will obviously need to be initialized first when we first call it. And then there's a few different variables in here which just handle where on the screen a message should be drawn, where the score should be drawn, the lives, the level number, and then obviously some timing delays here. So one thing to note in here is there is a bad manager here, which means we have to add one. So I will literally, for the bad manager, I will literally scale everything down, as this video is obviously quite long as it is. I want to dedicate most of the next video to in fact, I can literally just drop everything in here. And I will only implement the Mothership in here. So in the main game as well, to note is there are a number of sprites, although primarily the invaders themselves are actually constructed from tiles, as there are so many of them. Obviously we are limited with the amount of sprites we can actually have on the NES. I'll leave these other things here as not being proper tick timers for the moment, just to get our way to some action in here. I will explain all of this more in the next video. For now, I just want to get something interesting actually happening on screen. This is irritating. It's not giving the proper details for the errors here. Oh, it's because I've changed the data types for some of these. It's claiming that's something different. So we've got that one. So this here is basically the mothership spawn timer. As you can see, there's lots of bit flags going on here. So this first timer is in charge of spawning time, and the next one is the move one. And then there's another variable, another timer here for the normal baddie move-in time. Lots of timers. It doesn't matter. I'll fix loads of this. Some of these timers get changed through the course of the game. So all these errors are because I changed the timer type. That's what all of these are. I have to find where the old timer type was. I don't know if that's needed to even be external or not. In fact, I might just remove the all of the baddie code actually and fix this, or leave this for next week. This is going to be too painful to do while we're recording. As there's probably going to be a load of bugs here where I've changed everything. Yeah, I'm just going to do that. I'll delete most of this stuff here because it's just going to be a nightmare. Instead, I'll just leave you with the ability to move your player and shoot at the bases. This could be here for some time, otherwise trying to fix all this. Okay, that's built. Let's see whether the game actually plays. Is there actually any code in here? Why is that not working? Ah, because I'm not reading the key presses. Okay, let's try that again. There we go, there's our error. Let's see what it actually does. Okay, so we can run about. And you can shoot. There's no text being drawn for some reason though. Did I change a timer in here? So I think I might leave it there for this video. Haven't done all that I would like here, but there is a lot to cover. I have covered a lot already as well. So in the next video I will go more into detail on the actual gameplay code, and the core of it will actually be all of the enemy movements as well. So thanks for watching, and I will catch you in the next video for the finale. Thanks for watching.